All right, everybody, let's talk about some logical thinking and sort of formalizing our thought. Today we're going to be talking about both propositions and connectives. Those are the things that connect propositions together to make larger, more complex propositions. Truth tables, which are always helpful, especially for circuit design. And logical equivalences. So we're going to start kind of working our way towards what we're going to need for predicate logic and proofs later on. First thing is we want you to be able to develop your ability to communicate mathematically, basics of logic. Symbolic logic is not intuitive. It takes some time to think about stuff. And the more you can sort of connect what that is to sort of real life situations, it'll probably help. But there's still going to be some stuff in between where it's just like, oh yeah, well, I know that this is the equivalent, and I can almost forget about the actual real world implications, whatever the original logical statements are, A and B, I can kind of go away. I can just use the symbols themselves to make some truths and then sort of reinterpret it and see like, oh yeah, that does sort of make sense when I go back to sort of the real world circumstances I was thinking about. So we'll start with the definition of a statement. A statement, also known as a proposition, is anything that is declarative and either has a value of true or false. Could be either. You can have false statements, you can have false propositions. That's perfectly fine. In fact, that might actually teach you just as much as discovering something's true. But the idea is that it is a statement that can be proven to be either true or false. So 7 is odd. 1 plus 1 is 4. If it's raining, then the ground is wet. Our instructor is from Canada. These are all examples of propositions. They are things that will either be true or false. They can't be both, and there's got to be something. Some things that aren't statements, because they can't be determined to be true or false, would be things like questions, right? So like, am I okay? Am I cool? Or whatever. Like, that can't be proven true or false. You're actually asking for information. But something related to that, if you wanted to take that idea and phrase it as a proposition, you could say, I am cool, right? Make a statement one way or the other. Now that can be proven true or false, as much as one can define cool. A command, don't touch that, right? That is a command. It can't be proven true or false. You're demanding somebody do something. But that could also be rephrased as a proposition. You touched that, right? Now that's a statement that can be proved either true or false. Anything that contains what we call a free variable, we'll talk about free variables later when we get to predicates, but the idea that if there's a variable in it, then it can't be proven true or false until we know what that value is, unless we go through some larger predicate type stuff as opposed to proposition stuff. So the phrase x is even, right? That is something that's unprovable. It's neither true nor false because we don't know what x is. If we could find out the value of x, then we could actually make it into a proposition. 12 is even is a proposition. Has a value that's either true or false. Now normally, when we want to use propositions in symbolic logic, we represent that idea, that statement, with a single letter. So here we've got P equals Hamilton is a popular musical. Q equals Lin-Manuel Miranda is talented. Now again, as far as you can define talented, we could decide whether or not these things are true or false, right? They are statements that can be proven one way or the other. But now we can actually use them symbolically and just refer to those ideas as P and Q without having to actually write out, the whole English anymore. So statements can be made more complex, right? Propositions can be made more complex by sort of making these combined propositions. These things where you have multiple propositions that are connected together using something called a connective. We do these in English all the time. Connective in English is just a word, but obviously in symbolic logic it will be a symbol that connects and combines statements together. So and, or, not, if, then, if and only if. These are the connectives that we'll be sort of playing with. So below you'll see the names of the connectives as well as the symbol that we're going to use for them. If you want to try and remember the symbols, you only have to remember and, right? Because and kind of looks like an A, but without that cross thing. And so since you know that one's and, you'll remember that the one that's flipped over where it's a V is or. There's possibly another mnemonic that'll help you, but that's the one that I always think of as I look at them. Not is sort of a minus sign in front of it, but because minus already has a meaning, right? It's the negative of something as opposed to the not of something. Negative is a numeric idea. So in logic, we do sort of the same thing, but we put a little tail on it going down. That means not. So it's the negation. It's not. Implies sort of goes one direction. We say, if this, then this, right? So this implies this. That's why we use that arrow symbol. It goes one direction. If this is true, then I'm stating that this will also be true. If and only if is, and we'll talk about these as we get to them, it's actually sort of bidirectional. If this, then this, but also if this, then this. So the arrow goes two ways. Just to kind of explain the symbols, maybe give you some idea, maybe help you to remember the symbols. So if we say that P is the statement, you are wearing shoes, and Q is the statement, you can't cut your toenails, then we could combine those two propositions together into a larger, more complex proposition. If you are wearing toenails, then you can't, if you are wearing toenails, hi, I've been a human for many years. If you are wearing your shoes, if you're wearing shoes, then you cannot cut your toenails. This is now a larger proposition, which I would argue is probably true, but, I would still have to prove it, right? The idea is that I've now combined these two propositions. You are wearing shoes, which is in and of itself a proposition, and you can't cut your toenails, in and of itself a proposition. There could be other reasons you can't cut your toenails. But we've put them together to say, if you are wearing shoes, then you cannot cut your toenails, a whole new idea, just by using connectives with simple propositions. So, since every statement, right, is either just true or false, every proposition will evaluate to either a true or false value. There's only a limited number of possibilities for each of those. And so what you can do is take some of these and construct a truth table to look at these propositions. Either a single proposition or a proposition that's being held together by connectives, and that's kind of where it's a little bit more valuable. Obviously, the truth table for a single proposition without any connectives is just true and false, right? You have to find some other way of determining that. Those are the possibilities for any single proposition. But that idea of the truth table displaying all the possible, for all my P's, Q's, R's, all the different possibilities of combinations, how would that make the overall more complex thing look? Ends up creating that truth table. And so we can start by just looking at using simple connectives to put together, the simplest of sort of statements. And then we can kind of go on from there, using multiple connectives to create larger expressions. So the first connective we're going to talk about is not. Not is sometimes also called negation. And it's the easiest of the connectives because it has a very simple truth table. There's only, if you have for any proposition P, right, then not P is just, there's only one proposition you have to deal with. So proposition, there's only two possibilities, right? The proposition is either true or false. If the proposition is true, then not P is going to be false. It just negates the value. If the proposition is false, then not P will be true. Later on, we'll talk about double negation, the idea that the not of a not is the same as the proposition. Unlike in English, where you can use double negatives and it actually just makes it more negative. Not in logic. The not of a not, we'll get to that later. Point being, it just flips the meaning of a sentence. So if I say, you are not cool, well, so the proposition was you were cool, and I said you are not cool. So that just means the exact opposite. Make sense? The other connective, the next connective I should say, is and, which is sometimes called conjunction. And ands are only true. So ands, unlike nots only apply to one proposition or potentially to more propositions using parentheses. But and always has sort of two operands, right? There's two propositions on either side of the and. And so In this case, and is only true if both of the statements that it connects are true, right? And you can see that in the truth table here. If P is true and Q is true, then P and Q is true. But in every other possible combination of P's and Q's, P and Q is false. And that sort of makes sense. So if I were to say you finished your homework and you cleaned your room, that statement is only true if you actually did both. If you only did one or you only did the other, then it's not true. There's lots of examples of this in the real world, actually. If you get a check that's signed to two people and there's an and in between, then it requires two signatures. But if there's an or in between, it only requires one signature, which we'll get to later. But the idea is, it's and. Both of the things have to be true for the whole thing to be true. Or is sometimes called disjunction, and it's false only if both of the statements that connect it are false. This is what we'll call inclusive or. If you've taken circuit design or anything before, there is an exclusive or. It has a totally different symbol that we'll probably bring up later, but for right now, we'll just use inclusive or. And the idea is that this is, you can see it's true, P or Q is true for every single case except for the last one, where P is false and Q is false. In that case, the whole thing is false. The idea is here, I just need one or the other or both, but I need to have at least something. This is different than exclusive or, which is sometimes they'll use the soup or salad analogy, where you have a soup or salad that's included with your meal. You can choose one or the other, but you can't choose both. I suppose in the case of exclusive or, you have to choose something, which is probably not true of restaurants. You could just say, I don't want a salad or a soup. They'd be okay with that. They make more money. Regardless, it's not a great analogy. But the analogy for the one that we're looking at is inclusive or. You can pay with cash or you can pay with check. Perfectly fine. If you want to pay with cash and not check, that's awesome. If you want to pay with check and not cash, that's awesome. If you want to pay with check and cash, I suppose that's allowed. If you don't want to pay with either, you want to pay with credit card, okay, well now we've got a problem, right? You have to have cash or check, one of the two or both. That's all fine, but you have to have something. So my sort of real world analogy for or. The next connective is called an implication. You can think of it as an if-then, a conditional statement, and there's lots of different ways of saying this in English. If P, then Q. Sometimes we'll say P implies Q, which is where we get the idea of implication. Sometimes we'll say that Q is a necessary condition for P, or even sometimes P is a sufficient condition for Q, although that one's a bit more confusing. But the idea is, if this thing on the left is true, then I'm saying that the thing on the right will also be true, right? That's my statement. And it doesn't apply to other things where, like, the thing on the left isn't true. Well, then I know that I didn't make that claim, right? But if the thing on the left is true, then the thing on the right will also be true. And so this is the symbol and truth table for implication. If P is true and Q is true, then P implies Q is true, right? Because I kept my promise. I said, if P happens, then Q happens. And P happened, so Q happened. If P happens and Q does not happen, P is true and Q is not true, then I lied to you. I said if P happens, then Q will happen, and it didn't, so that statement is now false, right? The other two might not seem intuitive, but it kind of makes sense, right? The idea is that what I'm claiming specifically is that if the first thing is true, the second thing will also be true. So if the first thing is not true, well, I didn't make a claim about that. I didn't say anything about that situation. So you have not contradicted my statement, right? I never claimed what would happen if P was false. I only said what would happen if P were true. So there's no contradiction of my statement. And so that in that case, they are still considered true for the overall statement. So implication is only false when the first thing is true and the second thing ends up being false. This is sort of a oddly violent thing, but it's fine. Here I say, if you attack me, I will attack you, right? If you attack me, I will attack you. So if you attack me and then I actually do attack you, well then that's true, right? P was true, Q is true. I kept to my word. The result of P implies Q is true. If you attack me and I do not attack you, then that's false, right? I lied. You attacked me and I didn't attack back. My statement is contradicted, right? I said I would and I didn't. If you don't attack me, well, maybe I don't attack you. Maybe I do attack you. I never said that I wouldn't, right? I just said if you attack me, then I will attack you. But if you don't attack me, I might still attack you anyway, right? Like that's allowed. I never made any statements about that. So that is implication. But kind of a bad analogy. At some point I should find something that's a little bit less aggressive. Anyway, the next and last of the connectives we're going to talk about today is if and only if. So if and only if, which kind of gets abbreviated often as IFF, if and only if, it's actually two implications at the same time. I'm saying that P implies Q and also Q implies P. So this will only happen if this happens. So if and only if. The if and only if truth table basically works out to be that that statement is only true. So P if and only if Q is only true when the two things have the same value. So in other words, because it has to go both ways, if I do something and the other thing, if the P is true and the Q is true, then the statement is true. If the P is false and the Q is false, the statement is true, right? If P is false, if P is true and Q is false, then that's false. If P is false and Q is true, then that's false. Whenever they don't match, it's false. Whenever they do match, it's true. This is kind of going back to my previous violent analogy, but it was the kind of one that sort of made sense both ways. I will attack you if and only if you attack me. Now that's a completely different statement, right? The first one was, if you attack me, then I will attack you. But I didn't say what I would do if you didn't attack me. I might still decide to do it. This is kind of giving you a promise. I will attack you if and only if you attack me. Okay, so what you're saying is you're not going to attack me if I don't attack you. So if you attack me, I will attack you. If you don't attack me, I will not attack you. Those are where the statements are true. If either of us break our promise, you attack me and I don't attack back, or I attack you and you don't attack back, that's when the statement is false. Charitable, but false. All right. The last sort of concept for this week is logical equivalence. So logical equivalence mean that two statements or two compound propositions, however you want to think about this, are logically equivalent if they have the same true-false values for all cases. So if they have the exact same truth tables, then we can say that these two things are logically equivalent. A good example of this is the contrapositive. So the contrapositive is a statement that is logically equivalent. If we have the statement P implies Q, that is the logically equivalent thing of reversing the positions and knotting them. So P implies Q is the same as not Q implies P. They are the exact same thing, or they're logically equivalent. Later on, that will be helpful as we decide to do proofs, because we're going to need to sort of change the forms of things, kind of like algebra. We might need to like reverse some stuff and double negate some stuff, and we'll have some various rules to be able to do that with. But here's sort of my real world example. These two statements in English are both true. They are both logically equivalent. If you set your alarm, and remember I'm making an implication here, so if this is true, if you set your alarm, then you will wake up on time. So if that statement is true, then it's the equivalent of if you did not wake up on time, then I know you did not set your alarm. Because if you set your alarm, you would have woken up on time, right? It's the same statement. They are both true. So here we can say, if you set your alarm, you'll wake up on time. So let's assign these to letters, right, to some sort of symbol. So P is going to be setting your alarm. Q is you wake up on time. All right, so P is setting your alarm, Q is waking up on time. If that's the case, then here is the truth table. And the way you do truth tables when you have something that's a bit more dynamic is that you do first the propositions, like the bare propositions by themselves, P's and Q's, because we need to get every possible combination of P's and Q's. Usually you sort of do whatever the first one is, you do half truths, half falses, and then you sort of alternate going forward. And you can kind of see at least examples of 2s and 3s in the slides this week. But so here we have 2 examples, rows 1 and 2 of P being true, and then the last 2 are P being false. Now we need to alternate Q so that it's like when P is true, there's at least 1 true and 1 false for Q. All right, so we get that combination. And then when P is false, there's 1 Q is true, 1 Q is false. So those 4 rows ends up being every single possible combination of trues and falses for P's and Q's. By the way, if you were to add a third, I'm pretty sure you would realize that, oh, well, then I would need 8 rows, right? If I had 4, I would need 16. We're not going to do 4 today because, these slides are only so big. But regardless, I would need 16 rows to get every single possible combination, right? And so then what we do is we take every single element of that compound statement. So here, if you set your alarm, P, then you'll wake up on time. So P implies Q. And so that's our next column. P implies Q. Well, we know that if P is true and Q is true, then P implies true is true. In fact, we know that for any time P is false, P implies Q is true. So we got the bottom 2 rows. The only time P implies Q is false is that second row. P was true, Q was false. So now we have a new column that represents our first statement, the original statement. Now we have to sort of go back. If you did not wake up on time, then you did not set your alarm. So that is not Q implies not P, which means that I now need to develop those new things. Now, it might seem unnecessary to do not Q and not P. You can do that in your head, but formally, you would actually do the not Q and the not P, and then another column for not Q implies not P, right? And so the not Q is just the opposite of whatever the Q was. So Q is true, false, so not Q is going to be false, true. P is true, true, false, false, so not P is going to be false, false, true, true. Right? We're just flipping the signs. But now we can sort of look at not Q implies not P. Well, false implies false is true. True implies false is false. And false implies true is true. And true implies true is true. Right? The only times that implication fails is when true implies false, which means that P implies Q has the truth table true, false, true, true, and not Q implies P, or sorry, not Q implies not P has the exact same truth table, true, false, true, true. So you can actually use the truth tables in order to determine whether or not the two things are equivalent. There will be other methods later and some laws and principles that we'll bring up, but for right now. By the way, the converse of a statement is if P implies Q, then Q implies P. So Q implies P is the converse of the original statement. Converse statements are not logically equivalent. They might be, but you'd have to prove it, right? There's no guarantee that, that's true. For instance, going back to our original idea, if you set your alarm, then you will wake up on time. That's my original proposition. If you set your alarm, you will wake up on time. The converse of that statement in English would be, if you wake up on time, then you set your alarm. Well, I don't know that. Maybe, right? That's a possibility, but it's also a possibility that your mom woke you up. It's a possibility that a garbage truck woke you up. It's a possibility you're just a bad sleeper, right? You just got lucky. I mean, I don't know that you set your alarm just because you woke up on time. The original statement was, if you set your alarm, then you will wake up on time. But I didn't say anything about if you don't set your alarm. You might still wake up on time. You might not wake up on time. Oh, that's your household. All right, so then let's do a more complicated example, sort of embracing this idea of logical thinking and some of the stuff we've already discussed. So this is straight out of the book. If Aaron is late, then Bill is late. Okay, so that's one implication, right? If Aaron is late, then Bill is late. And if both Aaron and Bill are late, then the class is boring. So now suppose that the class is not boring. What can you say about Aaron? This is like one of those old school, they've actually moved it out of the GRE, but they used to have a GRE analytical, now it's like analytical writing, but it used to be these sorts of questions, right? And the idea here is that we can logically maybe conclude something. We just have to sort of think about it. And because it's going to get complex, we should probably think about it a little bit more formally with some math symbols and, you know, a little bit more precision. So let's define our propositions. Proposition P, Aaron is late. Proposition Q, Bill is late. Proposition R, class is boring. Seems straightforward so far, right? Now let's look at what that phrase, what the actual proposition is in English, and convert it into a sort of a, whatchamacallit, a formal math sort of complex compound proposition. So we're going to let S be the statement. If Aaron is late, then Bill is late. So we can represent that with P implies Q, because P was Aaron is late, and Q is Bill is late. So P implies Q. If Aaron is late, then Bill is late. And, now we're going to connect this with an and, right? If both Aaron and Bill are late, so P and Q, Aaron is late and Bill is late, then class is boring, R, right? So P implies Q and P and Q implies R. Now, with that logical expression, we've got our sort of our form. We can almost forget about what P's and Q's and R's stand for. We can just deal with the symbols, and then eventually we'll sort of dovetail it back to actually make some sort of a, you know, an insight. What can we say about Aaron? That's our question. So we're going to construct a truth table for S. And we're going to do that by constructing truth tables for all of the different parts of S, kind of like we did before, except this one's going to be a little bit bigger. Starting inside the parentheses and sort of working our way out. So S is equal to P arrow Q, I'm going to keep saying that, P implies Q, right? And P and Q implies R. So here are the different parts. I got P, Qs, and Rs. We're going to start by just those first three columns. I know I'm going to need 8 rows because I've got 3 different propositions I'm dealing with, and I've got to get every single possible combinations of, you know, different things. So the first proposition I'm going to break in half. So the first 4 will be true, the second 4 will be false. The next proposition, Q, I'm going to break into quarters, right? The first 2 will be true, the second 2 will be false, the next 2 will be true, the next 2 will be false. And that sort of ensures that I get every possible combination of P's and Q's. The last one I wanted to break into 8s, which essentially means, because there's only 8 rows, I'm alternating every row. True, false, true, false, true, false, true, false, true, false. You don't have to do it that way, but if you don't do it that way, it's going to be funky. This is the standard, right? Like, it's very clear you have gone through every single possible combination of P's, Q's, and R's. So now, our first chunk, right? Our first chunk is P implies Q. So now I can just do the truth table for my next column with just that part of S. So P implies Q. I don't have to worry about R because R is not involved with this segment. So I can just look at the first 2 columns and say, okay, well, true and true is true, true and true is true, true and false is false, true and false is false, false and true, well, anything where P is false is going to be true. So we're going to go trues the rest of the way down. There's only 2 falses, and that's in rows 3 and 4 where P was true and Q was false. It's only when Aaron was late and the other guy whose name I've forgotten, Ben? Bill. Bill, it's only the case where Aaron is late, but Bill is not late. That's when our statement is false. Okay, so now we can go on to the other side. The other side is, and we're going to kind of work our way in, right? So I'm not going to deal with the and yet. That's going to be at the end. I've already got the column for the left part of the and. Now I got to get a column for the right part of the and. So, and then the column on the right part of the and is actually an implication, but within that implication is another set of parentheses. So I'm going to get to that innermost parentheses first, which is P and Q, right? So Aaron is late and Bill is late. So if that's the case, then I can, again, just look at the first two columns. And is only going to be true when both P's and Q's are true. So the first two are going to be true and every other one is going to be false. Because every other one, other than the first two rows, one of the two is going to be not late. I almost said on time, but I feel like saying not late is or everyone's going to be late. You know what I'm saying. Again, I don't go back to the original yet. We can do that at the end. At the end, we're just sort of looking at the symbols now. So now I've got my P and Q value. So now I can say P and Q implies R. So this is my next column, where I'm kind of doing that segment. So P and Q implies R, right? I've got the P and Q column right next to me, and then I've got the R column, kind of the third column over there. But I can at least look at those two columns, and I can say, okay, so true implies true is going to be true. False implies true is going to be true. True implies false is going to be false, right? So the first two rows are true. I know that third row is false. Here are the rest of the ones. Wait. Oh, I was reading it backwards. Hi, that's embarrassing, but I'm not going to re-record this. Going this way, true implies true is true. True implies false is false. False implies true is true. False implies everything else is false. So I know that false, if the thing on the left is false, you're not making any implication about R. So everything else is going to be true. The only time that P and Q implies R would be false is in row 2. So now I've got both my sides for my sort of my most important and, right? On one side, I've got the P implies Q. That's the fourth column. On the right-hand side, I've got the one I just created, my last column here, well, until I get to S. And so now I can just look at that. And they're actually going the right direction this time, so I'm going to get this right. So this and, actually it's and, so it doesn't matter. So in the first row, true and true is going to be true. True and false is going to be false. False and true is going to be false. False and true is going to be false. True and true and true and true and true and true, all those are going to be true, right? And so this is what the column for, oops. Well, apparently I skipped a step. But, you know, it's going to be true. The only one that's going to be false is rows 2 through 4, right? Well, because rows 2 through 4 are false, that means that the statement is false. Now, because we, we presume that this thing is true, right? We're looking at the proposition that if, Aaron being late implies Bill is being late, and if Aaron and Bill are late, then the class is boring. If that is assumed to be true, then I don't have to worry about the ones where S is false. We can get rid of those because those are the cases where none of that is true. Right? We're trying to get an insight about Aaron, assuming that these things are true. So then there's also some I don't have to worry about, which are the ones where I feel like I skipped a step here. And so the only times we have to worry about it are the ones where they were both late, right? If one of them was on time, then that doesn't help us, right? So row 1, row 5, row 7, which makes sense, right? Like that's the ones where that's the ones where class was boring. We can eliminate those, right? These are the only two cases we have to worry about. It's the case where Aaron was late, and class was not boring. Wait. I want to go back some slides. Embarrassing, but I've lost my story here. Okay, so if Aaron is late, then Bill is late. And if Aaron and Bill are both late, then class is boring. Okay, so then here, then class is boring. We're saying if class is not boring, that's the premise. If the class is not boring, what can we say about Aaron? So we only have to deal with the ones where R is false, where class is not boring. Again, it gets confusing. We chose one with like 8 different rows. So if class is not boring, then I only have to deal with rows 6 and 7. We've eliminated all the other rows. So S has to be true and R has to be false. If that's the case, then what I can say about Aaron is that Aaron is not late, because in both of those cases, P is false, right? It is a logical, if somewhat convoluted, way of thinking that at some point I got backwards a bit, but, right, by kind of walking through that process, we can sort of eliminate some rows, different possibilities based on our assumptions, right? Based on the assumption that, the statement is true and the assumption that class is not late, we can say that if that's the case, then Aaron is not, class is not late. It's way too late. If we assume the statement is true and we assume the class is not boring, then we can state, that Aaron is not late. Anytime where that's true and class is not boring, Aaron is on time. That's the idea of logical thinking, and that's kind of the process that you'll go through to sort of combine and, figure out the value of each of those things. So with that, you've got your assignments, and if you have any questions, of course, send me a message through Canvas.